So let me try to be a little more formal about what's two functions, what's functions themselves. I was trying to give you some intuition last time. First of all, just something you've never seen formal definitions. So a Morse function has various different formal definitions, and why the word Morse two functions. Morse functions for a long time. Morse probably earlier. So Morse functions are Morse functions map F of some manifolds R, and such that it's smooth map. Smooth topology, and the way I like to say it is I like to say it in terms of local models. So such that for every point P and M, there's its coordinates x1 and around P, and some coordinates T, or let's say T around. This is just a single coordinate around f of P, and then with respect to which either f is equal to f equals 1 and 10 equals either sum of which minus f squareds, so sum of the squares, positive and coefficients, or or 2, I think I should put the other one first, f of x1 up to x10, just equal to x1, for a projection of the first coordinate. And so the first point is that this is actually the general situation. This may seem, if you haven't thought much, if you're not used to thinking about smooth topology, you might think this is kind of very special coordinates. But I mean, it is very special coordinates, but it's not very special behavior, because anytime you have, as long as the derivative of this map is surjective, then there will be some coordinate domain that's mapped surjectively into R, and then you can reparameterize things, so it's just that coordinate. So this is some standard topology. Standard smooth topology tells you this is what you have at a regular point. And then at a critical point, you can have all kinds of crazy behavior. But if you, this is the generalized satellite. I just think of this general satellite coordinate maps. So for in dimension 2, you either have in the domain, you either have x squared, that's whole, or sorry, x squared is y squared, or x squared minus y squared, that's a saddle, or minus x squared minus y squared, that's a cap, right? And you can have x cubed, you can have all kinds of things, but generically, this is what you expect. And so the theorem, all the way down, is that every manifold has Morse function on it, and furthermore, any smooth function is close to a Morse function. So you can just pick a random function, probably a Morse function, and that's the idea. And this is used to understand a lot about the topology of manifolds, and the Morse 2 function. The 2 comes from the fact that we are mapping to 2 dimensions rather than 1. And the reason to put the Rob Kirby and I started calling them this. Some people don't like it and just call them stable maps. And that's a great sense of what they are. And are only, well, maybe we weren't really so versed in the singularity theory language to use that when we first started thinking about it. But we're also thinking kind of we were inspired by higher category theory, categories, and then 2 categories and 3 categories, and there's some sort of sense in which this is a similar approach to higher Morse theory that goes with higher category theory. You know what that means. So you feel free to not like stable means, we'll take this down, but what stable means is that a function between 2 maps is stable if, when you perturb that function a little bit, you can pre and post compose locally with, actually, you pre and post compose globally with self-diffeomorphisms of the main range to make it look like what it was before. So in other words, up to some reparameterization, small perturbation doesn't change. Stable is cubed because small perturbation of it will change one critical point to two critical points. That's not stable. But f of x equals x squared, small perturbations of it can't make that critical point go. So that's, and so this notion of stability is important. An interesting question is whether stability is stable. So there's sort of one of the foundational questions in singularity theory is you define stability in a appropriate sense, what are the class of functions you're thinking about, and then you want to understand, you would like to say that stable is generic. That and generic, the proper way to say that is the space of all functions, and when it's stable, you want to say it's dead set or something. Okay, but probably so anyway, turns out stable isn't always generic, which is kind of mysterious and bizarre, but that phenomenon doesn't arise until it's mapping to dimension 6 or something. So it's weird, yes.
So you were saying like the x squared and x cubed. Like what exactly does perturbation is? Like,
Oh, okay, yeah, that's a good question. So if I have f of x equals x squared, so that's a map from R to R. Right? What I mean by a perturbation is actually, suppose this is actually f equals f0, and in the family f sub t, where t is, minus epsilon epsilon. So suppose I have a smooth one-parameter family of functions. So a perturbation of a function is really a smooth one-parameter family sort of passing through that function. And of course that can be many different perturbations, right? And so what I really want to say is that so a function is stable if given any one-parameter family of functions passing through that, for suitably small values of the parameter epsilon, you can reparameterize and it looks like nothing changed, right? And that's not true if f of x is x cubed, but it is true if f of x is x squared. Any one-parameter family passing through this function, x squared will very, very close to it, just look up to change the coordinates. That's a good, like, sort of elementary analysis. Not actually that elementary. Analysis probably for, or not really, that's calculus, right? Can you want to use Taylor's series and so on. Proving that x squared is stable as a function is kind of cool. Okay. So stable maps to R2, and so there's a theorem underlying all of this, which is that stable maps to R2 actually always have the following local models. Smooth smooth manifold R2, such that for every P domain, there's these coordinates. Okay, now I'm going to label my coordinates in a slightly strange way. T, x1, x2. And so really this is an n plus 1 dimensional manifold. I could call them x0 if it comes n, but I want to emphasize something. And coordinates P around P. Notice I didn't really ever reference it. That doesn't, it's u is equal to this, u is equal to that. I'm going to do the same thing here. I don't know why I need to get that discoloration here. With respect to which, either, I kind of wish I had done this the other word. Because I don't want to do the regular. So the first thing is f of t, x1 xn. T of x1. So it's just a projection onto the first two factors. And so this is what you should expect for a regular point of this function. If the derivative is surjective, then if the derivative is surjective, the map function looks like it's derivative to the coordinates, and then up to change coordinates, and you can then apply an element of GL to whatever pre and post causal linear maps to get into the projection of the first two coordinates. Or the next model, t x1 n is equal to, that's right, just t comma, and then the sum of plus or minus x squares. So what you should think is that the first, nothing happens in the first coordinate, and the second coordinate it's ordinary Morse function. And in a sense, that's the same thing here as well. Or the third case is t and t, still t, and then what I want here is, let me get this right, I want x1 cubed, and then I'm going to do a minus t x1, and then plus the sum for I equals 2 of 10 plus or minus x squared. I want to digest all of these. Oh, something you might wonder about is if you look at here, I just finished writing that down in the basic comments. So going back to the Morse setting, you might wonder of local as something in local model 2, and the answer is no, because by looking at the rank of the derivative. So here the rank of the derivative is 1, here the rank of the derivative is 0. Okay, so that's a simple invariant that distinguishes the two local models. You then might wonder, well, looking at local model 2, there's some pluses and some minuses. Could something with, first of all, something with 3 pluses and 5 minuses, it doesn't matter where, you can just, by changing coordinates, you can put all the minuses up front. So where the minuses are is not important. What might be important is how many minuses there are. And so how can you distinguish, how can you say that something with, say, 1 minus and 5 pluses versus something with 3 minuses and 3 pluses? Can you find local change of coordinates that turns one into the other? And the answer again is no, and the invariant there is the signature of the matrix of second partial derivatives, the hash. So you write down the matrix of n by n matrix of second partial derivatives, and it's a symmetric matrix, and it can be diagonalized, and the number of negative eigenvalues versus remember that's not going to change when you change coordinates. So there's this index here. Index equals the number of minuses in that thing. And so index 0 means a bold, means a minimum. Index 1 means one downward direction, some upward directions, and so forth.
When you said the derivative vanishes, that's just at the point P, right?
Just at the point P here.
Okay.
Another cool like multi-row calculus exercise is this index is also the index of signature for the partial derivatives. Signature of the matrix and signature of the sign. And the thing that so the signature turns out not to be well defined if you're not at a critical point. So in other words, if your derivative is non-zero, then you can find coordinates at to which you can get any signature you want there. But as soon as you're at a point where the derivative is 0, the signature is well defined independent coordinates, which is kind of like the calculus back. Okay, so going back here, there's one thing you might, if you allow orientation reversing changes, say that, then you can flip, you can switch 2 minuses and 3 pluses will become 3 minuses and 2 pluses. So you can decide whether the orientation of R is something you care about or not. Usually it is. Okay, going back to this picture, here, case 1 is a regular one. I need a matrix. Derivative of that 2. And if you look at both of these, and both of those, these are critical ones. And derivative of f has rank 1 in both cases. In other words, if you just look at, in these local models, you look at the derivative, you always get a 1 in the first place, right? To really partial with this coordinate with respect to t, and the derivative will be a 2 by something matrix, and you'll have a 1 at least somewhere, so you'll have some non-zero, it's not going to be a 0 matrix. I mean, this will be a 1 and then zeros everywhere else. So there's some, that notice that there's no rank 0 situations here, and the point is rank 0 is actually not generic. So these are actually generic. So another theorem is that course 2 functions exist in all manifolds, and they are generic in the sense that any given function, right, arbitrary. So then how do you distinguish these things? Well, actually, one way to distinguish them is going to, I don't want to make anything like that, but you can, geometrically, what we really want to do here is look at the image of, let's look at that. If you look at the critical value set, so what is it? So locally, let's see, in case 2, the critical of the crit, so that's the critical of this, the set of critical points, the set of points for derivative of 0 here is precisely the places where the x values are all 0. So it's set points. The local model, it's just the t-axis, and it's mapped by this map to the u-axis. So it's mapped. It's embedded to this f restricted to crits. So that is a smooth embedding. I mean, it just literally looks like the image. The image just looks like one. So this is okay. It's just that the image of this is the set of points where t goes 0. But in case 3, crits of f is more complicated, and I think I'm not going to think this is a good way to actually. Let's do the example in. We're going to focus. I'm going to focus on a case where, and you'll see the general thing, but in general, crits of f is a smooth submanifold. Still, it was a smooth one-dimensional submanifold here. And so here, so you might think, what's the difference? But the difference is that f restricted to that submanifold is no longer an embedding. So is a I'm going to say f of crits of f is a smooth curve with 1 pass. So smooth curve except at 1, except at 0, 0, where there is a C, one of my favorite words, semi-cubical. Semi-cubical is like half of cube, i.e. y squared equals x. Let's see, it's actually going to be, I claim it's going to look like x. In the UV coordinate, it's going to look like what's that? Something cubed equals something squared. If he has, u has to be positive, okay? So u cubed equals v squared. That's right. Or if we use the semi-cubical, then v equals u to the q semi. Plus or minus. Semi-cubical cusps are really strange, are somehow generic in another sense that I don't know how to put my finger on, but they arise in, if you have a cusp appearing in nature, it's a semi-cubical cusp. They're the stable cusps in some sense. You see them when you see light reflected inside your coffee cup onto the surface of the coffee. You just have coffee in the morning. I don't know how that. The answer for why you see semi-cubical cusps there is in the back of Arnold's book on mathematical methods and classical mechanics. I don't really understand it, but they appear in different projections of the genre knots, etc. And so that's the point, is that's how you kind of distinguish what's going on here. So let's zero in on the, well, okay, there's the definitions, and I'll try to, since Jeff may be back on Friday, to try to have a clean ending to what I do. So maybe I will, let's see. So I claimed that last time I was drawing more just two functions on surfaces. So surfaces meaning n is equal to 1. So there was really just this factor and this. So good, maybe we can try to digest what I was doing there. If I want to consider, let's look, actually, first let's consider n equals 1 in both cases. So for Morse function, that means we just got f from a one manifold R, and there's two local models. There's three local models there. There's f of x, or f of x equals x squared, or f of x equals minus x squared. And so that's what you see if you have some like that mapping to, you usually think of Morse function as mapping. And so there's your critical value. This is index 0, this is index 1, and this is so pictures. That's relatively straightforward to understand. However, one thing I do want to say is, if you want to think about putting a knot in bridge position, it ties back to what Jeff well, not K or not or length. 3 is in bridge position. If, so I think of the knot K as a submanifold S3, and if you consider so S3 sits inside R4. So R4 has coordinates, let's say x1, x4, x1, x2, x3, x4. Let me not call them x's because those are my local. Let's say y1, y2, y3, y4. If when I take the function y4 restricted to k, that's mapped from k to r. Then that is Morse, first of all, with y4 all index 0 critical points, so you schematic picture of my schematic picture of S3, my schematic picture, this is coordinate y4, mapping to R, this is 0, 1, and -1, and then I have this not, and what I don't want to have is a max or a min up here or a max down here, and then I could think that the mid-level 3 sphere, mid-level 2 sphere in this case, that the equatorial 2 sphere cuts it into a trivial tangle above and a trivial tangle below. And then, it's a good exercise to try and figure out why, how do I know that this is sufficient relative to the trivial tangles? Right? How do I know that? How do I know in this situation that the stuff that sticks up here actually bounds, what do you call it, a membrane? What do you call it, a membrane? And one way to get that is to take the standard metric on S3 and take the gradient vector field for this function y4 with respect to the standard metric. Well, anyway, there's a downward flow. You don't need to say gradient, just the downward flow that decreases y4, it stays on the 3 sphere, and that downward flow will necessarily, well, be careful. You could have something where that downward flow, something else is stuck there. So you want to argue that you can perturb things a little bit, and if you perturb things appropriately, then you can, those downward flows will sweep out like this. So that's the idea. There's something you said there. That's the idea of what bridge position is. And that's to set you up for a way to think about bridge trisector position. So now we're doing n equals 1 for the Morse 2 function. So this is how, this is my training to think of topology and Morse theory, and that's how I think of a bridge position is. It's in Morse position, and all the zeros are below and all the ones are above. And that's kind of a useful picture to have for lots of things. And the point is, how do you put something in bridge position? Well, you just throw your knot in there in general, and it does crazy stuff. And it does. And then whatever your knot does, and then you first perturb it a little bit so that this function is Morse, which is, by the way, a little bit. I said just a function can be perturbed to be Morse, but here we want to, it's a little bit more subtle because I want to change this function, the composition, not by changing y4 as a function, but by isotoping k around, and then therefore, like some would say that you can find an isotope to achieve Morseness. But anyway, you can, and then you want to argue that you can pull all the, if your index 0 is too high or index 1 is too low, you want to argue that you can pull these down. Or figure. So now n equals 1 for Morse 2 functions. So the first one, so I'll just say x and y instead of x1 and x2. So one is x equals xy. So that's so there I just have a surface, and I think of the blackboard as R2, and I have the surface, and I'm just projecting the surface on the board, and locally I can, locally, another way of saying it is locally, that's special about it being dimension 2 in the domain. Same thing here, locally it's 50 more. And 2 is that that's why. Well, let me remember my definition of Morse. I had only 2 conditions, plus or minus, and now I split them into 3, the plus or minus into 2 cases. Maybe I should have called this 2.1 and 2.2, because now I have to say cases here. So this is f of xy is supposed to, sorry. Okay. t comma plus or minus x squared, so there's a 2.1 where it's t minus x squared, and there's 2.12 where it's that tx is t comma minus x squared. And there's a 3.1, which is f of tx. No, there's only a 3 point. It's just a 3. F of tx equals t comma, and then there's x cubed minus tx. So I want to think about that. This is this is the one we need to understand. But first of all, these are the foliates. Because what's going on here is that you've got your domain, you've got your t in your x direction, and then you map that over to u goes with t, but then the x direction maps to x squared, so in it sideways, that's the image of the u to t, and then the squared. So it's folded this way, and the other model is the other model for this one. Now here it turns out that actually these are the same up to change. So you can just rotate, even if you want to preserve orientation, you can turn this model into this model by if you exercise, if you apply rotation by 180 degrees in domain and range, that turns this model into this model. So if I rotate by 180 degrees here, I don't, it looks like the t is going backwards, and then I rotate by 180 degrees again, and then I get this picture. So these are actually equivalent updated. So these are equivalent to oriented coordinate change. So they're really the same. And it's called a fold for the obvious reason. And so this one is the one that we want to study. And but the other point, the other picture you should have in your head is this second coordinate is a function just of the second variable. But in this case, that's also the second coordinate can be thought of as a one parameter family of functions of the second variable. So you can think of this as a t-parameterized family of functions of x. Okay? And so to think about that t-parameterized family of functions of x, you think about the function x cubed minus tx. And two cases, three cases, so if t equals 0 in the middle, that's x cubed. Graph of it. If t is bigger than 0, then you're subtracting some x, which means you're locally it's going to look like minus x in the origin. You have this, and that's two critical points, and t is less than 0. It's still a cubic, but it doesn't have any critical points at all. So no critical points, one critical point, two critical points. And then if you take all these pictures and tilt them this way and stack them up, that's your picture of the turn this way. That's your picture. So this is t and x, this is the picture of the domain, and then what I'm really doing there is embedding the surface of R3 and then projecting. So like drawing this picture here. If you like, this should really be augmented by saying there's a way of embedding the surface in R3, meaning forward and then projecting. But so I'm going to do the same idea here. I just want to take so I have, well, let me draw the singular focus first. I did this before, and so then you want to think of this function as happening the image of the t-axis is right there in the middle. So that's the picture, and this is the locus or locus running in the middle, critical locus here. And the critical locus back here is actually, I think it's a straight up parabola, right? Parabola. Correctly. That's the set of, this is the set of points that map to those points. And but there's this one point where there's something special. Okay, so that's what those cusps were I was trying to before. But one, maybe what I should say before I move on, to go back to the more general setting, a slogan for Morse 2 functions is locally they look like time, comma, time parameterized family of Morse functions. And if you have this sequence of functions here is a Morse function on R, except at one point. And this is sort of the generic behavior as it's moving through from one Morse function to another, it's birth, canceling pair for points. So that's what you're seeing here is birth, canceling pair. I mean, there's a local model, but if you wanted to say, what's a local model here at this point? If you want a local model at that point, you pick sort of coordinates like this, and in those coordinates, you can see a fold. There is a fold. So that everywhere except this point in the domain, you can use these fold models. So that's the fold, that's the cusp. The moral is that the critical locus is a one-manifold, and the image of the critical locus is going to be an immersion. It's an immersion because somewhere else there may be another fold that comes through here. The image might be immersed, except there can be more sheets, except it's immersed with semi-equivalent cusps. All right. So I'm going to right now claim whether or not we proved it, at least for. So I want to write down a claim that is the bridge trisection version of the claim I had that says a knot link is in bridge position if when I restrict the y4 function, if I get a Morse function, that's I want to write that same claim, the equivalent claim down for a surface in S4. So surface S in S4, which is contained in S5, which has coordinates y1 and y5. Oh, in that thing I raised here that said take the y4, I could have done y1, of course, nothing special about y4 or any other direction you choose to project on, except that I just think of projecting the last one. So we do the same thing here. If is in bridge trisecting position, if when I take y5 restricted to S, that's not from S, no, not to y5, sorry. Now I'm wishing I had done y1 in the first place. Because I always think when I think in this case, I think of projecting on the first two coordinates. So anyway, it doesn't matter. Okay, forget about this. If y1 comma y2, this is a function from R5 to R2, therefore from S4 to R2. And if I think of that as a function I'm restricted to S, function from S to R2, if this is a Morse 2 function, with the following values. So to elucidate properties, I need to give a slightly more, let's see. Let me name some subsets of R2. First of all, so digression for elucidating properties, let R2 equal A1, equal A2, equal 3, and follows, so that's one. A1, A2, A3, and again, I regret going counterclockwise, clockwise, or whatever, but I'm learning it's Jeff's problem, sort out. So he wants to, and so these are angled in 2 by 3. So that doesn't really matter, but I'm just being explicit, just some, so this is a trisection of R2. And I also want to, and then also consider the theta function, the angular function from, well, technically it's R2 minus the origin to the circle, which I put as 0 to pi mod equivalence relation. And I'll let, I'm not sure what I need, but I'll let R theta be the ray that makes that angle theta. So this is R0, this is R 2 pi 3, this is R. So A1 is bounded by R0. So the following properties are going to be in reference to this bit of notation here. Okay, the first, let's see, maybe let's just do convenience. Let Z contain an S be the set of critical points. I call it crits, so whatever, but I don't want to. Critical points of this function y11. Just call this function f. F. And I'll let C. So remember, the set of critical points includes fold points and cusp points. The folds from this one manifold and the cusps are points on that one manifold. Let C be Z be the set of cusps. And then, so the condition I want is that, the first thing is that if I look at Z intersected with any of the AIs, it should be, is a,
You mean f of z consecutive?
no, but that doesn't make sense to do that, yeah.
The image.
Actually, here, let me say something simpler. So if I take the function, right, so for each theta, R sub theta is going to transverse to f of z, except at the cusps, where R sub theta is like a tangent. The cool thing about a cusp is there's still a well-defined tangent direction. Okay, so a cusp, even though your map is not immersed, there's still a tangent direction. Okay, so I'm requiring that the cusp be, I think I get this time. And then the second thing is that, so this means the picture now is that I have green. And now I have these. Now, currently you might have something like this, but I'm sure we can rule that out. Just drawing something crazy. This isn't necessarily realistic. Okay. And so that's the first thing. So every, that's what you see. all these rays are transverse. In particular, that means things don't double back, right? Now, the second thing I want is that each component of Z intersected with F inverse of AI for each I. So I take one of these components of, so I've got Z, so it'll break up in a bunch of components, has at most one constant. And actually, that's all. Oh, and last thing is all cusps point out. You know, you don't want, so this is first of all bad. Okay. That's bad. And the second thing that's bad is something like this. And this is supposed to be sort of analogous to cleaning things up. This is supposed to be some kind of like a maximally cleaned up version of the Morse 2 function. So I claim that, so that the theorem is proved time, so you can all prove it, or you can think about how to prove it or something. So I claim that with just these conditions, you can actually work out and see that you will satisfy, well, bridge trisector position. Then what I do is finally, to get the actual bridge splitting, bridge trisection of the surface. Bridge trisection is, what is that pronunciation, BI and SI? Anyway, I'm supposed to have pairs, right? I'm supposed to take S4, comma, S, and split it as a function of BI, B1, S1, B2, S2, B2, S3, something like that. These are supposed to be balls, these are supposed to be pieces of the surface, and I let you get this by letting BI equal F inverse AI equal Y1, Y2 inverse of AI inside S4. So you think of this Y1, Y2 as a function from S4 to R3, and SI equals F inverse of AI. And so things to check are that when you take the inverse image of these sectors in S4, you get balls. And with this extra condition on these cusps, you actually get the distributed disks. The only thing you get is disks. And so to digest this, if you want to digest this further, and I don't give a lecture on this, which I'm really not, what you should do is compare this theorem to the torus example I did last time and claim that all the pieces are there to be able to do this. Time out? No?